Here we're asked to calculate the pH and the concentration of various strong bases. Strong bases dissociate completely into OH minus plus the conjugate acid. Okay, so I wrote down some relationships here that we're going to use. And first off, the pH is given by the minus log of the hydrogen plus concentration. But there's another relationship that we can take advantage of, and that's the pH plus the pOH equals 14. Or in other words, 14 minus the pOH equals pH. We can find the pOH from the concentrations of the OH minuses that we have up there. And the pOH, very similar to the pH, its pOH is equal to minus log of OH. So once we find that, we substitute it back in, we'll get our pH. So let's calculate the pH and the OH concentration if we have a known concentration of potassium hydroxide. We have 0.182 molar potassium hydroxide. Okay? And so recall that there's only one OH on there, so it's going, since it's a strong base, it's going to go to complete dissociation just like this. And so for every mole of KOH we have, we'll get a mole of OH minus of the hydroxide. So if that's the case, we've already know what the concentration is. We merely have to find the pOH, and from that we'll get the pH minus log of the OH minus concentration, and that's equal to the minus log of this, 0.182 molar, which is an OH, and that gives me a pOH of 0.740, but what we really want is the pH, and so the pH is going to be 14 minus 0.740, which was our pOH, and that gives me a pH of 13.3. Here we're given the mass of a strong base in a solution. So we're going to have to convert this into the molarity of the solution, and then we'll find the concentration of hydroxide ion and the pH. So first off, the molecular weight of KOH, if we pull out our periodic chart, we'll see that it's 56.1 grams per mole. And so if we have 3.165 grams of KOH, then a mole of that is 56.1 grams, and that gives me 0.0564 moles of KOH. And since it's 1-to-1 for KOH for hydroxide, that's also equal to the moles of hydroxide that I have. So now we got to get our volume in our correct form. We know that 500 milliliters is the same as 0.500 liters. And so we get the molarity, we have the moles, we have the liters. So our molarity of hydroxide is 0.0564 moles of hydroxide divided by 0.5000 liters. And that gives us 0.1128 molarity in OH concentration. Now we can get our pOH, and our pOH is the minus the log of that concentration, so pOH is minus the log of 0.1128 molar, and that gives us 0.948 pOH. Finally, we can get our pH, and our pH is 14 minus this, so our pH is 14 minus 0.948, and that gives me a final pH of 13.1. Here we're going to calculate the OH concentration and pH of a solution that we're going to dilute. So we need to find the concentration of the diluted solution, and we use our dilution equation. C1V1 is C2V2, and we solve, and we'll end up with 10 milliliters over 500 milliliters times 0.0105 molar, and that'll give us a new concentration of 0.0105 molar. Now that's for the calcium hydroxide. But recall that this has 2 hydroxides, so really we're going to have to multiply this times 2 to get the number of moles of OH minus we have. And so we'll go ahead and find the molarity of our OH minus, and we'll skip a little step here and we'll say, well, that's 500 milliliters is 0.5 liters, and so we've got 0.0105 molar in the calcium hydroxide, but there's 2 hydroxides that come off. That will give us the moles of OH minus, and we're going to divide by the final volume, which was 0.500 liters, and this will give us our molarity of hydroxide in this strong base solution that's just been diluted, and that gives me 0.0084 molarity in OH minus. And we can get our POH, and that's minus the log of that 0.00840 molarity OH minus, and that gives us a POH of 2.078 POH. And finally we can get our pH by remembering our relationship that 14 minus the hydroxide minus the POH is equal to the pH, so that's 14 minus 2.078 POH, and that gives me 11.92 for a pH. So what happens if we mix together 2 solutions of strong bases? Well, when these are dissolved, they're going to be completely dissociated. So this barium hydroxide is going to produce 2 OHs, this sodium hydroxide is going to produce 1 OH. So we just have to calculate up the number of moles of hydroxide we have and get a final volume. So first off, let's just get the number of moles, and it's 20.0 milliliters times 0.0105 molar times 2, because remember we're calculating the OH concentration, so it's times 2 because there's 2 OHs, and that gives me, pull out my calculator here, 20 times 0.0105 times 2, and that gives us 0.42 mole OH minus. Okay. Next up, we have 40 milliliters of the sodium hydroxide, so that's 40.0 milliliters times 8.2 times 10 to the minus third, and there's only 1 OH, so we leave it like that, and that's 40 times 8.2 exponent 3 minus is 0.328 moles OH minus. Now we just add them up, plus 0.42 gives me 0.748 moles OH minus, and we have a total over here for our volume, and so our final molarity of the solution is 0.748 moles divided by 60. These are, by the way, millimolars. Millimolar divided by 60 milliliters, and that gives me a molarity of 0.125 molar in OH, and we'll get our POH from that, and it's minus the log of 0.0125 molar, and we'll do minus log, return our answer, and we get 1.904 for POH, and finally the pH is equal to 14 minus that, and that gives us a final pH of 12.1.